For people that are already here, we will wait a couple more minutes for other attendees to coming back from their one-on-one meetings. All right, let's get started. Hello, everyone. Welcome to Section 2B of ISMM. I am Paul Tsai from NVIDIA, and I will be chairing this section for the next couple hours. Before we start, I would like to briefly remind everyone the format of the section. So for each paper, we will first play a pre-recorded paper presentation, and then we will have a live Q&A section with the authors. For people joining us in Zoom, please use the raise your hand feature so that I can let you speak and interact directly with the author. For people watching live streams on YouTube, you can also ask questions on Slack and the author will be able to answer them live too. Okay, so the first paper is about exploiting asymmetries in both within a memory technology and across memory technologies to improve performance. This paper titled exploiting intra and intra memory asymmetries for data mapping in hybrid tiered memories. And the authors are Shihao Song, Anam Das, Nagaranjan Handasamy from Drexel University. And let's play the video.
Hello, everyone. My name is Naga Kandasamy, and on behalf of my co-author Shihao Song and Anup Das, I'll be presenting a recent work on exploiting inter- and intra-memory asymmetries for data mapping in hybrid memories. So we motivate the problem using a hybrid memory system shown here, comprising of DRAM and phase change memory, or PCM, which is a type of non-volatile memory technology, NVM, along with some key observations related to such a system. So in the hybrid memory system, the DRAM and NVM can be configured as separate modules, as shown in the figure on the left-hand side, or as shown in the figure on the right-hand side. The DRAM can be configured as the write cache for an NVM-based main memory. So the hybrid memory system introduces some asymmetries in terms of both performance and reliability. So for example, DRAM memory has fast read and fast write times and practically unlimited endurance, but incurs a high energy overhead to maintain the volatile contents in memory. PCM, on the other hand, has fast read times, but slow write times and limited write endurance, but it's energy efficient given the non-volatile nature of the memory. So we would like to exploit the fundamental asymmetries that underlie these memory technologies to improve performance and reliability of a DRAM non-volatile memory hybrid memory system. Let's now discuss a few related issues here. So this slide shows from a page allocation perspective, a system such as Nimble starts from a random allocation of memory pages and dynamically migrates these pages between DRAM and NVM based on program behavior. The objective is over time to migrate write-intensive pages to DRAM and keep the read-intensive pages in PCM or non-volatile memory. So for the shown benchmarks, if we profile the number of times a page is migrated between DRAM and PCM during program execution, we see that on average about 67% of the pages incur more than one migration during execution. So this leads to increased energy consumption and reduced performance due to migration overhead. So we would like to see if rather than starting with an initial random allocation, we can place a page within the matching memory segment during the initial allocation itself to save on the migration cost. So to do this, we can use the concept of a first touch instruction. In a virtual memory system with demand paging, these FTIs are the ones that generate the page faults with their first reference. And when we profile these FTIs, we see that there are very few of them relative to the number of instructions in each workload. So on average, only 17% of FTIs touch pages in a program, which however serve over 90% of the memory accesses. So the key idea then is to profile these FTIs at one time and predict the access intensity of a newly referenced memory page, whether it's a read-intensive page or a write-intensive page, and place it in the matching segment during initial allocation itself. So the final set of observations relate to internal memory architecture. Memory banks in DRAMs and PCMs are organized as an array that's shown here, comprising of bit lines in the horizontal direction and word lines in the vertical direction. So in a non-volatile memory, for example, each bit is represented by resistance of a cell, low resistance representing logic 1, high representing logic 0. And this resistance is read or programmed by a driving current through the cell using a peripheral circuit that consists of sense amplifiers to read and write drivers to write. Now, given such a setup, there are two major issues to note. First, the peripheral circuit is much larger than the size of the cell. It can be seen here by the plot down the bottom. And to amortize the cost per bit, many cells are connected to a single peripheral circuit via these bit lines. So in our case, we will assume that each bit line in non-volatile memory contains 4,096 cells, and the DRAM contains 512 cells. The second issue is the parasitic components, shown by the lumped RC model here, are a major source of high latency in both DRAMs and non-volatile memory for long bit lines. In the case of NVM especially, they contribute to high voltage operations, which negatively impact reliability. The figure at the bottom shows the voltage drop or IR drop as a function of the number of cells along the bit line for these three operations, set, reset, and read. So the further a cell is from the peripheral circuit, the higher is the IR drop. So the peripheral circuit must then compensate for this drop by driving more current through the line, causing reliability issues for the circuit. So given this issue, the idea is to introduce isolation transistor in each bit line to allow the bit line to be partitioned into near and far segments from the perspective of the peripheral circuit. We'll show how the simple addition achieves low latency in both DRAM and PCM memories and improves reliability of PCM memory. Next up is an overview of our method that we call MNEME, after the muse of memory in Greek mythology, comparing our approach against two other state-of-the-art approaches, TL DRAM, in which segmented bit lines are used in DRAM-based main memory to tier the memory into near and far segments. The other approach is Nimble, that we looked at previously, that migrates pages between DRAM and non-volatile memory, but without the bit lines being segmented. Our approach intelligently places the pages within DRAM or NVM memories, and furthermore, within each of these memories, it places them in the appropriate tier, near or far. based on program behavior. So in terms of getting a segmented bit line, one isolation transistor per bit line is used to segment the word lines. So the segment connected directly to the peripheral circuit is called the near segment, whereas the other is called the far segment. The isolation transistor can remain open when cells of the near segment are accessed. And the isolation transistor must be closed to access cells of the far segment. As the table above shows, cells in the near segment can be accessed faster using lower bias voltages due to the reduced parasitic on that path, improving both performance and reliability. This plot shows the execution time of the 15 workloads that we considered on a hybrid memory with segmented bit lines. The results are normalized to execution time of a baseline design where bit lines are not segmented. We can see that by simply introducing memory tiers by creating segments is not enough. We only get an average 2% performance improvement relative to baseline. So we also need an intelligent page management policy at the OS level to efficiently exploit these inter and intra-memory symmetries. So the page management policy is the high-level overview shown here. The program is broken down into fixed intervals or phases, in our case, 100 million instructions each. During each phase, we profile the first touch instructions based on accesses to the pages that they touch. And this instruction is used from the previous phase, is used in the next phase to decide the initial placement of all newly referenced memory pages of subsequent phases. The figure at the bottom shows the journey of hot and cold pages through the tiers of the hybrid memory. This includes page migrations between tiers of the same memory unit and page migrations across tiers of the DRAM and NVM memories. Let's quickly walk through a simple example of how profiling first touch instructions helps with page placement. Let's assume that no profile information is available at the beginning of program execution. And let's say that at some time, the program counter A1, that's the instruction that resides at location A1, causes the initial page fault, loading page A into the far memory segment. As the program executes, the load instruction located at address A2 generates a page fault, and then page E is loaded into far memory segment. And similarly, the store instruction at A3 generates the page fault, and page Q is loaded into the far memory segment. So these instructions at addresses A1, A2, and A3 are the so-called first touch instructions. Now assume that as we iterate through the outer for loop, the load and store instructions that are at A2 and A3 generate numerous accesses to E and Q. We record them as FTIs that induce large numbers of accesses to any page that these instructions may load in the future. That's important. And therefore, later on, when the load instruction references an address that requires page F to be loaded, we will load this page into the near memory segment. Similarly, R will be loaded in the near memory segment when the store instruction generates a page fault for R. Similar to the stores and loads, branches and jump tables also contain FTIs that can be predicted to load frequently accessed pages. So this slide shows a high-level implementation overview. The memory controller maintains an FTI table that contains the program counter values of all the access-inducing FTIs. Supposing the load instruction located at address 108, there's a virtual address, generates a page fault. As part of the page fault handling process, we first look in the FTI table. In this case, it's a hit in the table. And so the memory access is predicted to be the memory page is predicted to be access intensive, and the page fault handler allocates this new memory page, shown in orange here, to the near memory segment. And now let's consider the case of the instruction located at virtual address 116. Now, upon the page fault, we look in the page FTI table. This results in a miss. So this FTI is unknown, possibly referencing a non-access intensive memory page. So the handler allocates the memory page to the far segment that is shown in blue here, while tracking the number of accesses that made to this page, generated by this page during this analysis phase as part of the AIR, or access intensity record. So at the end of each phase, From the AIR, the top unknown FTIs in terms of number of accesses are then inserted into the FTI table. Then that will be used to predict and place all new pages loaded due to this FTI to either the near or far segments. So this FTI table then is constantly updated with new access-inducing FTIs that are uncovered as the program executes. Now, using the FTI table, we can place a new memory page to a specific tier or segment within DRAM or NVM. We can also select the specific memory type, DRAM or FVM, by maintaining two FTI tables that distinguish between read and write intensive pages. And the AAR is also extended to record the number of read-inducing and write-inducing pages each FTI touches. The FTI table itself is implemented as a Bloom filter, which is much more energy efficient data swap. Right? The next step of the process is to reduce memory channel occupancy during page migration between tiers of the same memory. We focus on PCM. So in PCM, the bank is implemented as a collection of partitions that operate, this is important, mostly independently. They share peripheral circuits in the form of sense amplifiers to read and the write drivers to write. And for the peripheral circuit within the PCM bank consists of a sense amplifier here to read and the write driver to write. They're connected to the Bitlines using these transistors M1 and M2. The write driver itself can be viewed as a collection of two components, the pulse shaper logic that generates the current pulses necessary for the cell set and reset operations, and the verify logic, which verifies the correctness of these operations. And these two components together service requests to the bank using a scheme called program and verify. We can then make a simple circuit modification by introducing an extra transistor shown in orange here, which can be configured when needed to transfer data from the sense amplifier to the write driver directly. So we can program the data that is read by the sense amplifier to a different row at the bank using the write driver without having to utilize any external memory channels. So this reduces the power consumption costs as well as overhead. Note that to migrate pages across different memory units, we would still use the memory channel. This shows the interaction between the architecture and the operating system. Inside the memory controller, there's a separate read and write queues to buffer requests to the memory module. The address mapping block here, based on if there is a hit or a miss in the FTI table, selects the correct timing and voltage parameters based on the memory segment that needs to be accessed. So if we hit in the FTI table, we'll select parameters, the timing parameters to access the near segment. If there is a miss, we will choose the parameters for the far segment. So in terms of evaluating approach against existing methods, this slide summarizes the simulation parameters we have. It's a cycle-accurate x86 multi-core simulator, front end based on PIN. It's configured to simulate 8 out of order cores. The DRAM is configured with 128 near Bitlines in the near segment, and 384 Bitline cells making up the far segment. Similarly, PCM main memory is configured with the 512 Bitline cells in the near segment and 33584 cells in the far segment. And power and latency values for the DRAM and PCM memories are based on Intel/Micron's 3D X-point specification. So this table summarizes our approach against the baseline approaches, which are the Intel and IBM architectures, along with Nimble and TL DRAM in terms of system performance, energy consumption, migration overhead, and lifetime reliability. So this slide shows the execution time achieved by both Nimble and our approach against baseline for 15 workloads. The baseline here allocates a page randomly to a free physical address. Pages are not migrated between DRAM and PCM during program execution, and Bitlines are not segmented. As we can see, Nimble achieves better performance in baseline by an average of 7% due to Nimble's policy of migrating hot pages from PCM to DRAM. In certain cases, however, as we can see with Blender and B-Waves, their performance is worse than baseline because of the page migration overhead. On average, the execution time achieved by our approach is 21% higher than baseline and 16% higher than Nimble. This is due to the segmented Bitline architecture as well as more intelligent initial page placement that reduces the number of page migrations. In terms of energy consumption, again, Nimble has about lower energy consumption baseline only by about 2%. Now the reason is because of the any potential energy savings due to accesses going to DRAM rather than to NVM are overshadowed by page migration overhead. On the other hand, energy consumption of our approach is about 18% lower than Nimble, and achieved primarily due to reduction in the number of page migrations that would otherwise use the memory channel, and also facilitating inter-segment data transfer and inter-segment data transfers with reduced channel capacity. Finally, we improve the endurance-related lifetime by an average of 20% compared to Nimble because of these extra tiers created inside each memory using isolation and transistors. Pages that are not frequently referenced can now stay in DRAM or segment regions for more time before they're migrated to PCM. This reduces PCM writes that improves the endurance. So let me finish up by summarizing key contributions of the paper. The basic idea is to exploit inter and inter-memory asymmetries for data mapping in PCM and DRAM hybrid memory by introducing isolation transistor in each bit line to create tiers in PCM and DRAM banks. And therefore, it creates performance and reliability asymmetries that a intelligent page allocation policy will exploit. We use FTIs, or first touch instructions, to predict the access intensity of newly referenced memory pages in a program and allocate these pages to a matching memory tier during their initial allocation. This reduces the number of subsequent page migrations that may be necessary. We also introduce simple circuit modifications to migrate pages within tiers of the same memory type or same bank without occupying the memory channel, leading to further power savings. In terms of performance evaluation, we've shown significant reduction in execution time overhead, an average of 21% reduction in execution time compared for the spec CPU benchmarks compared to baseline. And we have also shown significant energy reduction, 19% in average for the spec benchmarks over baseline. So I will stop here, and I am happy to take any questions that you might have. Thank you.
All right, let's virtually thank the presenter, and apologies for we are going to change the schedule a bit to move the Q&A section for this paper to the end of the session 2B. So in other words, we're going to move on to the next paper directly now, and we will come back to the questions people you may have for the previous section, for the first paper. Okay, the second paper in this section is titled Understanding and Optimizing Persistent Memory Allocation. This work is from University of Rochester, led by the first author, Wen-Tao Chai. This paper presents a correctness criterion for persistent allocators and introduces a lock-free persistent allocator that pays almost no performance overhead for persistence. Let's play the video.
Hello. Hello, everyone. My name is Wen-Tao Chai. Thanks for being here. Today, I'd like to share our work on understanding and optimizing persistent memory allocation. The work was done at the University of Rochester with Hao-Sung Wen, Alan Bido, Chris Shaw-West, Mohammad Hadayati, and Michael Scott. So, non-volatile memory DIMMs are already commercially available. This byte-addressable non-volatile memory also has competitive performance to DRAM, which makes people to think of directly placing persistent data in the memory. There are indeed a lot of ongoing works about persistent data structures and in-memory databases, most of which require dynamic memory allocation. So generally, in persistent memory programming, memory regions appear in the file system as files, and during execution, processors map these files into their virtual space and directly issue loads and stores to the data without page buffering. However, due to volatile caches and random writes back, explicit write back and fence instructions are required to ensure ordering of stores. Once regions are mapped in, the process can retrieve data from persistent roots, which are a set of pointers located at some statically determined place within the region, usually at the beginning. In order to easily manage free space, an allocator that survives failures are also required. So, for an allocator to be persistent, there are mainly two issues to handle. One is to ensure the failure atomicity of allocation and deallocation, which means after a crash, an allocator operation either happens entirely or no set effect is should result in. This is usually ensured by some kind of logging mechanisms. Second is about how to avoid failure-induced memory leaks. Imagine if a crash happens between the allocation of a new node and the attachment that links the node into the data structure. Then, in the wake of the crash, the application no longer has reference to the node, but the allocator may still think it's allocated, and then a permanent memory leak happens. One way to solve that is to combine allocation and attachment as a single failure atomic operation, malloc2. And so, and we can do a similar thing to deallocation and detachment to form free-from. Another way suggested by Makalu is to keep conventional malloc-free interface. And after a crash, it issues a garbage collection tracing from persistent roots. By comparing and investigating, we notice two interesting things. First, non-standard malloc2 free-from API isn't ideal to solve memory leaks for at least three reasons. First, it's hard to port existing code. Second, it doesn't work well with thread local pointers, since you also have to make them persistent and retrievable. And after a crash, you need to get them back, either deallocate them or finish the rest of the operation, and link them into global structures. The similar story happens in applications which need some kind of free lists. For example, in non-blocking data structures, limbo lists are used to temporarily hold blocks that to be reclaimed, but not yet safely to do so. After a crash, we also need to bring them back and deallocate blocks in the lists. This can be very annoying for programmers to handle by themselves. But on the other hand, applications must already keep data persistently reachable, since they need to retrieve them in the future executions. Second, allocator operations don't have to be persistent in order. In the wake of a crash, all we care about the allocator is about which parts of the region are used and which are not. So it's unnecessary and slow to eagerly persist allocator metadata to non-volatile memory in every operation. So we began to think that the existing persistency models maybe are too strong for an allocator. And then we introduced recoverability as a weaker but sufficient correctness criterion for persistent allocators. So informally, an allocator is recoverable if after a crash, it is able to bring itself to a state so that all and only the reachable blocks are allocated. By properly tracing the reachable blocks, allocators can be made recoverable without persisting much. And after a crash, we can reconstruct metadata based on reachability. And so that both failure atomicity and failure-induced memory leaks are properly handled. Here, in terms of failure atomicity, I'm using attachment and detachment rather than allocation and deallocation as the durability point. Then we implement write lock as what we believe to be the first lock-free recoverable allocator. Based on lock-free transient LR lock, it persists only size information of blocks to enable conservative garbage collection. There's no need to log online, and in the wake of a crash, it reconstructs allocator metadata based on offline garbage collection. By default, the conservative garbage collection is used, which treats every 64-bit aligned word as a potential pointer. Write-lock also allows the programmer to optionally specialize a filter function for a particular class to mitigate the false positives in the type unsafe language, such as C++, as we used in our project. So here is an example to show how a programmer may specialize a filter function for binary tree. In the left is the definition of the tree node class, which contains two pointer fields, left and right. And in the right, to implement a filter function, you just call visit for every pointer field, and that's it. Where visit is just an interface that's provided by write-lock. Also, in order to have pointers valid across executions, we adopt position-independent off-holder as a smart pointer and encourage the programmer to use it in data. This 64-bit pointer stores the offset of the target from the pointer itself, and is self-contained. So there's no need for fixed address or lookup of base address. This figure demonstrates how it works. There's an off-holder, say located at 0x70, and its value is 30. So the real address it actually points to is A0 during dereferencing, which is equal to the sum of 70 and 30. In the design of write-lock, we separate the data and metadata into three regions. Superblock region contains real data, and each superblock is a chunk of blocks in the same size. The superblock region is lazily consumed as a sparse file. So you can create a very big one, but only use, say, the first 1 GB to begin with. Whenever the 1 GB is not enough, you can expand the in-use space just by a single atomic computer swap operation on the used file field. Descriptor region contains descriptors in which the case descriptor describes the status of the case superblock. There is a static 1-to-1 mapping between descriptor and the superblock because the size of every superblock is the same. All other metadata, such as free list, persistent roots, size classes, and dirty indicators, are all stored in metadata region. There's also a thread local free list per each thread in order to make most of operations synchronization free. They are not shown in the figure, but you can imagine that. So only fields marked as bold and red in the figure are persistent, while all others can be transient and reconstructed during recovery. For fast restarts, though, all regions are flushed during normal execution, during normal exits. So the experiments were conducted on 2 sockets of Intel CPUs. Each one has 20 cores and 40 hyperthreads. We compare RedLock with the 2 state-of-the-art persistent allocators, PMDK and Makalu, and also 2 fast transient allocators, LR-malloc and JE-malloc. In a particular benchmark obtained along with MNEME persistent transactional memory, we also test the built-in allocator of the transactional memory, which is a persistent hybrid of Horde and DL-malloc. The experiment has 2 parts. The first one is macro benchmarks, which are widely used for testing allocators, including Horde and Makalu. Also, we compare the performance of persistent applications use different allocators. Here, Vacation is a simulated online transaction processing system. The one we tested was obtained along with MNEME persistent transactional memory. Also, we run the well-known in-memory database, memcached, under the YCSBA workload with 50% writes, 50% reads. This is the figures, this is the results about macro benchmarks. The red curve, as you can see, represents RedLock. In all figures, RedLock is at least an order of magnitude faster than the other persistent allocators, which are yellow curve and blue curve. And the only one curve faster than RedLock is representing a transient allocator, JE-malloc. So in terms of persistent applications, RedLock also provides a better performance and better scalability than other persistent allocators in most of cases. Here, RedLock is also represented by the red curve, as you can see. So, in conclusion, based on our observation, we introduced recoverability as a weaker but sufficient correctness criterion for persistent allocator, and notice that allocator metadata can be mostly transient and reconstructed according to reachability. Further, we implement RedLock as the first recoverable lock-free allocator. It's fast, scalable, and it's open source on GitHub. So at last, I create a table to compare RedLock with PMDK and Makalu, which are the state-of-the-art persistent allocators. So to avoid memory leaks, RedLock takes a similar strategy to Makalu, plus an option of filter function to mitigate false positives. To ensure failure atomicity, rather than doing some logging, such as in PMDK and Makalu, RedLock reconstructs most of the metadata during recovery according to reachability. For pointers to remain valid across execution, RedLock uses position-independent pointers and keeps them within 64 bits. Finally, RedLock also provides a lock freedom liveness, while the other 2 uses locks. That's all for today's talk. Thank you so much, and I'm happy to take questions.
Right, that's thank the presenter virtually again. And for anyone that has questions, please either use the raise your hand, there's a raise hand feature in Zoom, or you can ask question in the Slack channel. I think people are typing, and I think I would use this opportunity to ask a question first. So thanks for the great work. My first question, do you expect the programmer to always use the filter function correctly? And what happens if they make mistakes in such case?
We assume that filter functions are correctly implemented if the programmer is willing to use it.
Mm-hmm.
Yeah, so if it's incorrectly implemented, it can, incorrect thing would happen.
I see. Okay. My next question would be, so can you comment on the recovery overhead of RELX scheme, and have you done any experiment studying such cases?
Yes, we had a subsection in the paper about recovery. We haven't been able to directly compare it with, say, Makalu or PMDK. Yeah, but the experiment was designed in a very similar way. Yeah, I had a description in the paper. If you are still interested, we can talk either offline or yeah.
Okay. Thank you for your answer. Yeah, just curious about that. There's actually one question from the Slack channel. This is Khan. She asked, PMDK also provides transaction support for the allocator. Does your work have any transaction capabilities? And if not, how difficult would it be to adapt it to a transactional setting?
Because our RELOC is based on reachability, we think it's naturally compatible with any use cases, including within transactions.
Mm-hmm.
Yeah.
Okay, let's see if there's other questions around, and we'll give people maybe a few seconds to ask. All right, if not, let's thank the presenter again, and we'll move on to the next paper. So the third paper is titled Alligator Collector, a latency optimized garbage collector for functional programming languages. The authors are Ben Garami from WellType LP and Laura Dees from University of New Hampshire. Let's play the video. So I'm not
of Haskell, a lazy.
I'm sorry, there's some technical issue. We will restart from the beginning.
And good. Hello, my name is Ben Gamari, and I'm a compiler engineer at WellTyped, working on the Glasgow Haskell compiler.
Hi, I'm Laura Dietz. I'm an assistant professor in computer science at the University of New Hampshire.
And today I would like to speak about a garbage collector for the Haskell programming language that my collaborators at WellTyped, Laura, and I have been working on for quite some time now. So in general, garbage collection has been a pretty well-studied problem in the imperative world. However, it's a bit less clear how well these approaches work in a language which strays from this imperative model of evaluation. So today we'd like to provide a case study examining how a simple concurrent mark and sweep collector works in the context of Haskell, a lazy, pure, functional programming language. So first, why might one expect that a language like Haskell would place different demands on its garbage collector compared to, say, Java? One reasoning centers around a facet of Haskell's evaluation model, namely its non-strict evaluation semantics. We can see this demonstrated in this pseudocode example. In a traditional strict setting, the binding of var on line 1 will immediately evaluate its right-hand side, potentially performing a non-trivial amount of work in the process. However, in a non-strict language, like Haskell, binding an expression to a variable does not imply evaluation. Rather, this will only happen if the binding is later needed. GHC, the Glasgow Haskell compiler, which is the case that we will be examining today, implements these non-strict semantics by way of lazy evaluation. So, for instance, in the case of this present example, the binding of line 1 will give rise to the allocation of a heap closure, which we call a thunk, represented here, which captures the state of the suspended computation, which we can later resume once it is needed. So for instance, on line 5, we see here that if it's a Monday, print var, and in this case, that will result in what we call entering an entrance of the thunk, where we first check whether it has yet been evaluated, and if not, we jump to its entry code, call in the compute nth prime function. This will return a result, and we will then take that result and use it to replace or update the thunk with an indirection pointing to the end result. This can then be used by later occurrences of var, avoiding the need for reevaluation. Now, lazy evaluation in this way gives us two things. It provides work avoidance, allowing us to avoid evaluating var's right-hand side at all if var is not called for, and sharing. It allows us to evaluate var once and reuse that result over many occurrences. More generally, non-strictness allows the user to decouple reasoning about the semantics of their program from its evaluation strategy and its operational behavior. This enables things like opportunistic parallelism and the ability to define control flow structures at the library level. And these features give Haskell much of its appeal. However, purity and pervasive laziness do present some challenges for a garbage collector. While pure functional programmers tend to make little use of explicit imperative-style mutation, we rather use persistent data structures, and these can tend to produce high rates of allocation with lots of short-lived garbage, as versions of a structure are created, then modified by in the process creating a new version of the structure and throwing away the old version. Moreover, while there is little explicit mutation in the source program, thunk updates, like of the sort that we saw in the previous slide, are exceedingly common. Consequently, the garbage collector implementer must keep in mind some three principles when evaluating their design. We must be mindful of allocation costs, since allocation is performance critical, even more so than in many imperative languages. We must keep in mind that much of allocated data will be short-lived, and we must keep in mind that An expensive barrier on thunk updates in particular would be problematic, since these are very common and tend to occur in the inner loops of some programs, especially when compiled with minimal optimization. Now, before our work, GHC had a generational copying garbage collector, and this allowed fast bump pointer allocation and dealt well with the high rate of garbage churn produced by functional programs. However, this collector was ill-suited to server workloads with even moderate latency requirements, particularly with large working sets due to its copying nature. Now, this was the context in which we undertook the present work, where a client approached us with using Haskell in a latency-sensitive server application. They asked for our help in tackling the long major GC times which they observed in their application. And along with this gave us sort of some insights into their challenges that they saw in not just running their Haskell applications, but also deploying and maintaining their Haskell applications. In particular, GHC is a batch compiler, and consequently, unlike just-in-time compiled languages like Java, many Java implementations, recompilation poses a significant deployment challenge, having to worry about which arguments, what version of the runtime system a particular executable is compiled with in deployment is a headache that our client expressed they'd rather not have to worry about. And so consequently, we worked under the constraint that any new collector or runtime feature must be possible to enable at runtime without the need for recompilation. Now this, of course, constrained our design space a bit, precluding the use of intrusive barriers that would potentially regress the existing throughput-oriented copying collector, and precluded any change in heap layout, which would require recompilation of mutator code. Meanwhile, of course, we needed to impose near zero overhead on users of the existing throughput-oriented collector. So taking these considerations into mind, we quickly settled on an approach which would allow us to focus on the long pause times incurred by major collections while retaining many of the beneficial performance characteristics of our moving collector. Namely, we would retain generational collection, using the moving collector for young generations, but then using some other bounded latency collection strategy for older generations. This kills several birds with one stone, as the mutator continues to use the moving nursery, avoiding the need for recompilation and providing efficient allocation. Further, it can handle high garbage loads due to its generational nature, and it allows us to minimize implementation complexity, as we can reuse much of the work and optimization that has gone into GHC's existing copying collector. Use of, for the old generation, we opted to use a non-moving heap, which would facilitate concurrent mark and sweep collection, allowing us, in principle, constant time pauses. In particular, we borrowed heavily from the work of Ueno and Ahori and their 2011 and 2016 ICFP papers, where they described a non-moving heap structure which, based upon a family of non-moving subheaps, each servicing allocations of a fixed size, and alongside these subheaps, such metadata to enable snapshot at the beginning, concurrent collection in the style of Yuasa, and reasonably efficient allocation, thus making them appropriate for functional programming languages. The concurrent mark and sweep prescription follows a fairly standard recipe. Here we see a timeline of what such a collection might look like. Here we see two Haskell threads indicated by these green boxes running on two separate operating system threads, which in the Haskell world we call capabilities. These are happily running along, allocating into their moving nursery, when we, at some point, realize that we've run out of heap and we need to perform a major generation collection. When we realize this, we stop the world entering a phase of collection which we call the preparatory pause. And here we start evacuating data into the non-moving heap. This evacuation we perform reasonably aggressively, since we are unable to reclaim objects which participate in intergenerational cycles. After we've evacuated and scavenged the young generations, we collect a snapshot using the aforementioned subheap metadata structures, enabling, as I said, UASA-style snapshot at the beginning concurrent collection. We will then enable a write barrier, again following the model of UASA, a barrier on deletions within the pointer deletions within the non-moving heap, and allow the mutators to resume. At this point, we've entered the concurrent phase of collection. And during this time, mutators can perform minor collections. These are moving collections of the young generations, and these may promote into the non-moving generation as the non-moving generation is being collected or marked concurrently. These minor collections are stop-the-world events. This is why we opted not to implement a full on-the-fly major collection scheme. Minor collections must stop the world and generally greatly outnumber major GCs, so consequently the benefit of implementing a full concurrent non-stop-the-world major GC scheme would be relatively minimal. I should further point out that stack marking poses a particular challenge for Haskell server programs, as these can use tens of thousands of green threads, each with unbounded stack depth. For this reason, we were marking these threads stacks during the preparatory pause would be unacceptable for latency reasons, and consequently our collector implements a mechanism, which we describe in our paper, to allow stack marking responsibility to be safely shared between the mutator and mark thread. While as the mutators continue execution, the concurrent mark thread is running in the background, marking the non-moving heap. Once we have marked what we believe to be the entirety of the live data in the heap, when the indicated by the mark queue running dry, we then signal another stop the world event and enter what we call the pre-sweep pause phase of collection. During this time, we collect the remembered sets that were collected by the mutators as a result of the write barrier that we previously enabled, and mark their contents, and perform a variety of other sundry bookkeeping before we disable the barrier, allow the mutators to continue, and move into the concurrent sweep phase of collection. Now, as I previously mentioned, we have a write barrier in the style of UASA for our snapshot at the beginning collection scheme. This write barrier attracts pointer deletions, so it will cover cases like this, where if we have an object A, which holds a reference to another non-moving heap object B during the preparatory pause, we must ensure that B is marked in the course of marking. And to ensure this, we incur this barrier where during the concurrent phase, mutators which mutate objects living in the non-moving heap, such as this case here where we've mutated A to rather point to C, must ensure that the old value of the pointer that they have mutated ends up in their thread local update remembered set. These are thread local structures, and they are such to avoid contention between threads. However, we periodically flush these to the global mark queue to ensure that we do not build up an unbounded amount of work that must be then resolved during the pre-sweep synchronization phase, stop the world phase of collection. Happily, the majority of deletions covered by this barrier are thunk updates, which are already covered by GHC's existing generational write barrier, and consequently, this barrier incurs relatively little cost over that which we already pay. The generational remembered set, again, a write barrier maintained by a write barrier, is a feature of GHC's existing generational collector, and goes largely untouched by our design. Again, it tracks intergenerational references. This is a barrier in the sense that you would find in most generational collection schemes, tracking references from old generations into young generations. In particular, closures in this set are scavenged during minor collections, ensuring that young generation collections can see reachability, even if a object is only referred to from the old generation without sweeping, or rather without tracing the entirety of the old generation. This poses an interesting challenge due to our concurrent sweeping phase, since there is the possibility that a minor GC occurs while a sweep is underway. In this case, if A was found to be not reachable during the concurrent mark phase, it may be swept. And meanwhile, we may attempt to scavenge A due to its presence on the generational remembered set. Since A is not a live object, there's no guarantee that it's a valid closure or that it points to valid closures, and consequently, this poses a hazard for scavenging. We avoid this by sweeping the generational remembered set during the pre-sweep pause. Sadly, there are a number of details which we lack time to cover in this talk, but we'd refer you to the online appendix and the paper for further discussion. Briefly, indirection shortcutting is a somewhat Haskell-specific mechanism which allows the collector to short out indirections that are produced by thunk updates. Selector optimization is a sort of allows the collector to perform a small amount of eager evaluation, avoiding some classes of space leaks. Thread stack marking I had previously mentioned, and we have various heuristics and barrier treatments to ensure efficient treatment of mutable primitive types, such as IO refs that are widely used that are often found in performance critical points in imperative Haskell code, imperative style Haskell code. However, we'd now like to turn our attention to mention some findings from our empirical study. This study consisted of a suite of benchmarks, most of which are modeled around server workloads. Some of these are well-recognized benchmarks within the Haskell community. Others are benchmarks of our own writing, and others are client workloads. We'll cover only a few here in this talk, but you're again referred to the paper for further details. Our first question that we had was, are garbage collection pauses in fact shorter? This is the goal of our work. And we're happy to see here that the answer is more or less yes. So here we see this is the LRU cache benchmark as described in the paper, looking at garbage collection pause time distribution across 4 different runs of the benchmark. In particular, we see 2 runs of the non-moving collector and 2 runs of the old throughput-oriented copying collector. The maximum heap residency of this program is approximately 8 gigabytes, and consequently we see that major collections, and in the case of the moving collector, can produce pauses, tail pause times of over 1 second, whereas in the non-moving case we tend to limit worst case pause times to approximately 30 milliseconds. We also see here that there are 2 different configurations which we run this benchmark, one serial and one 8-core, perhaps more realistic server configuration, and scale the request rate appropriately. This is an HTTP server, and so consequently we can easily measure end-to-end response time as seen by an out-of-process client. We here use the WKT2 HTTP workload generator to characterize this distribution. And we see that this nicely reflects the change in garbage collection pause time that we saw in the previous slide, with worst case latencies in the moving case being over 1 second, and again, the non-moving collector exhibiting typically tens of milliseconds in the worst case. This is roughly a factor of 40 improvement in latency, but of course this is an asymptotic improvement, so we would expect this factor to grow as the heap size grows. In the case, another question we wanted to address was how much memory we lose due to fragmentation. One strength of the copying collector is that fragmentation is typically of little concern. By contrast, our non-moving heap structure is subject to both internal and external fragmentation. To characterize this, we look at a quantity which we call occupancy, which we define to be the fraction of non-moving heap, of memory rather, allocated to the non-moving heap, which contains live data, that is not slop within a memory allocation cell, after sweeping. So this characterizes both internal and external fragmentation. And we see here in this benchmark, which is a run of the Glasgow Haskell compiler building a large library, that over the entire course of the run, the occupancy tends to stay around 75%, which we find to be acceptable, given that in the case of a copying collector, during the evacuation stage of collection, this occupancy would be approximately 50%, since the collector would have to double the size of the resident live data size during evacuation. There's a few different markers here that probably ought to be discussed. So we have here the pink points characterize the overall occupancy across all subheaps, that is across all object size classes, and the black markers look at the 3 most populous size classes in isolation. In the bottom pane, we see the overall live data, and we see that in this case the benchmark has approximately a few gigabytes of live data for most of its run. Finally, the last question that we wanted to address was how much does this non-moving allocator cost? In particular, the bump pointer allocation used by the copying collector represents near best case as far as allocation cost is concerned, whereas our free bitmap allocator used by the non-moving collector, it will likely incur, one would expect, a significantly higher cost. While we tend to isolate the mutator from this cost by use of the, again, moving nursery for mutator allocations, this will nevertheless affect minor collector performance. So we look at, to characterize this effect, we look at the minor collection pause time distribution, comparing the copying and non-moving collectors across these 2 benchmarks, search and map test. And we see indeed that the pause time of minor collections, again, this is a minor collection, not major, so these are much shorter, but nevertheless, we see that this pause time does increase by roughly a factor of 2 to 3. And in particular, we note that the larger pauses are due to increased fragmentation within the non-moving heap. While these in absolute terms, these pause times are relatively short compared to the tens of milliseconds pause latency target that we're trying to target. We'll note that minor collections are very common, are very frequent, and consequently can be a significant tax on mutator performance. So consequently, this does affect the overall throughput of the application. However, we would note that in the server workloads that we had looked at, in particular the LRU cache benchmark, we note that there is very little effect on overall mutator time, mutator CPU time, and this is true for most of our server workloads. We saw anywhere from 5 to 10, in some cases 15% on most server workloads. However, less server-oriented workloads did exhibit much greater regressions in throughput, and this is something that we're currently investigating. So, in conclusion, we describe some considerations influencing collector design for pure functional languages, and describe a generational moving, non-moving hybrid collector design targeting batch-compiled Haskell. We evaluate an implementation of this design present in GHC 8.10 on a variety of workloads and show that our concurrent mark and sweep collector can yield significant improvements in mutator responsiveness on typical server applications with moderate impact on throughput. However, we show that there is an impact on throughput, especially in highly mutating and highly allocating workloads. And there's clearly room for improvement in allocator performance in our particular implementation. But we'd be happy to take questions or hear your ideas on how to improve our design. And at this point, we'll thank you for your time and open the floor for questions. Thank you.
Right, that's virtually thank the speaker again, and thanks for and joining us in the Zoom session. So if you have questions, feel free to ask it in either in the Slack channel or using the raise hand feature here. But before that, I will take this opportunity to ask Ben a couple questions. So this is a really interesting paper. Does the mechanism ask anything specific to Haskell or its language features?
Yeah, so it's a fair question. And it's something that in hindsight probably should have been made a bit more apparent in the talk itself. So ultimately, the design was largely enabled by the fact that in Haskell, because we have almost all mutation arises via way of these thunk updates, it becomes much easier to meet our goal of enabling this compiler without recompilation, which was again one of the design requirements. As well, there are a few issues that arise only in Haskell that we discuss only briefly, not in the talk at all, and make brief mention of the paper. That is, we have an optimization known as the selector optimization and also shortcutting of indirections, which primarily arise due to, again, the laziness, indirections that arose due to laziness in the latter case. And selectors are sort of a bit of eager evaluation that we use the runtime system, the garbage collector, namely, to perform to eliminate some classes of space leaks that can arise in pure functional programs. So these features are all things that you likely wouldn't find in another language, or at least a non-pure functional language. But frankly, the mark sweep collector itself is, in the end, what you might find in any other imperative language. It's really what we layer on top and the sort of optimizations to enable high number of threads and these additional optimizations. I might also say that there's a few heuristics that we use to determine promotion. Well, what sorts of objects should be promoted into the non-moving heap and can be promoted into the non-moving heap for that matter, that may not be as applicable in other, again, non-functional languages. But yeah, I guess that may answer the question.
Yeah, that's a great answer, and thanks for that. We actually also have a question from Slack channel. Actually, two questions. The first from our General Chair Chen asked about how would you approach the problem if the code can be recompiled?
Yeah, that's another great question, and it's something that I've thought a bit about. So we ultimately had to make a few compromises to achieve this lack of recompilation. For one, I do wonder whether it might be so the barriers that we have obviously are designed in such a way to minimize the effect on the existing collector, the throughput-oriented collector. And frankly, if we were to allow recompilation, we'd probably want to make these barriers completely optional. There are a few barriers that I just finished saying that almost all barriers appear in the update frame entry code that is used for thunk updates, but there's actually two cases where that's not true. You'd likely want to remove those two cases that do appear in mutator code. Otherwise, as far as how it would affect the design itself, that's a bit less clear to me. Whether this whole mark and sweep approach it would still be applicable. I think that's something that I would need to think a bit more about, but I'd be happy to discuss offline. Obviously, there's a variety of alternative approaches that would allow incremental or even concurrent compaction or another scheme that might be more suited in the case that you can allow recompilation. I've not thought enough about this to know.
Yeah. Thanks for the answer. We have actually 2 more questions coming in, and question asks, could be any benefit on using this GC design in an actor-oriented language like Xlr, which is strict but allows lazy evaluation?
Yeah, that's oh, sure. So yeah, that's a good question. I'll admit I'm not particularly familiar with Elixir, but it sounds like it's a mostly strict language that sort of has opt-in laziness, and I suppose in that case, it's likely that you're going to see a fair bit more mutation in sort of standard programs. If you do those programs that don't take advantage of the lazy evaluation notion. And in that case, it would probably be a bit harder to, as I said before, sort of fit in both the lack of a recompilation requirement and the barriers that we would require in that case. So I'm not sure that that's true, but I'd be interested to know more about the case of Elixir and what its design might imply. Can happily take this offline.
Okay, the next question is actually from Hans. You mentioned the size of classes are part of 2s. So did you also encounter significant internal fragmentation? So
no, that's something that we were.
So the answer is yes. Yes, it's powers of 2.
Oh, they are powers of 2. Yes, that's right. Yeah, that's correct. But we didn't see the sort of fragmentation that I was fearing. And in part that might have worked out because GHC objects in Haskell tend to be quite small. So it's typical to see data types of 1 or 2 or 3 fields, and fields are inevitably word size in GHC Haskell. So the amount of slop that you sort of see in that case, especially where you have a 4-word closure that fits nicely into our powers of 2 heap structure. And most of those, by accident, I guess you might say, a large fraction of our objects are precisely that. So,
and you should mention, I mean, so like large objects that are kind of like beyond a certain size, are kind of like handled outside of the heap.
Of course, yeah, we do the usual.
So like this is sort of like where the regularity of object sizes sort of like also comes in here, which then reduces the internal fragmentation.
Yeah, so the large objects are handled separately as is usual, and then the fact that our size distribution happens to work out somewhat nicely perhaps saves us there.
All right, thanks for the answer again. And we will wait a few seconds to see if there are any more questions, because I saw someone typing in the Slack channel. And if anyone want to raise their hands in Zoom channel, this will be a good time. All right, thanks the presenter again. Thank you, Ben, for answering these questions. And we're going to move on to the last paper in this section, which is about verifying the functional correctness of a segregate fruitless single-threaded malloc-free system, and has the title Verify Sequential Malloc-Free. It's a joint work from Princeton University and Stevens Institute of Technology. Let's play the video.
Hello, I'm Dave, and I'll be speaking about verified sequential malloc-free, joint work with Andrew Appel. Now that there are tools for proving functional correctness of C code, we should prove correctness of important programs. You are looking at part of our correctness lemma for the function malloc. It says the function bodies were correct with respect to a resource-conscious spec, assuming correctness of the functions it calls, including the mmap system call. The proof script directs the proof assistant to construct and validate a proof. Some steps do forward symbolic execution through the code, covering all execution paths. Other steps perform logical inference, for example, applying a lemma or invoking an automated prover to reason about assertions concerning the heap. In this talk, I will explain what we did and outline the prospects for verifying an industrial strength implementation. In the paper, you can read about prior work, bugs and surprises we encountered, and more about the verification effort. General-purpose malloc-free systems should provide high performance over a wide range of workloads. There is no optimal solution, so they're highly engineered, using complicated algorithms and data structures and low-level code. This slide highlights pointer arithmetic and casts in our implementation of a function that cuts a large chunk of memory into a linked list of small blocks to fill one of the free lists. We use a conventional array of bins structure, or size segregated free lists, and we use the mmap system call for large blocks. We must reason about things like pointer alignment and prove that the code has no undefined behavior according to the C11 language standard, and of course, function satisfies its functional spec. Who cares? Well, all programs rely on the correctness of core system components like allocators and the compiler and hardware, crypto, etc. So these days, bit by bit, we're building up an ecosystem of verified software components, especially these core kinds of components. Even attempting to prove correctness tends to winnow out bugs and helps lead to improved interfaces and designs. If we have reproducible proofs, this empowers engineers to evolve and improve the software, carrying out aggressive optimizations and so forth, with the confidence of correctness based on proof, covering all executions rather than just some tests. In this work, we give the first machine check proof for an implementation with expected constant time performance. We're implementing the standard malloc-free API. Our implementation has been used by other verified code. We are doing the proofs at the source level in the Coq Proof Assistant, and in particular the VST Floyd system for reasoning about C code. This is part of the verified software toolchain based on CompCert, a verified C compiler. That, so ultimately, our proofs compose with the CompCert proof to give us proof of correctness of the compiled assembly code. And by doing this, we've demonstrated the feasibility of verifying a real concurrent malloc-free implementation. This work has been carried out as part of in the context of the Deep Spec project, in which operating system components and other components are being verified and composed together, and hardware included. VST itself has been previously used to verify crypto components and some other things, which I don't have time to talk about. VST implements separation logic. Well, that's a program logic, so when we make claims about programs, they have the form of a HOR triple, a precondition, command, and postcondition. What it means is, if the initial state satisfies the precondition, then it's safe to execute the program. It won't exhibit any undefined behavior or crash. And if it terminates, then the final state will satisfy the postcondition. Here's an example, very simple one here, in which we are assigning the value z to the memory addressed by p. The precondition says that p pointed to x before, that was the value at address p, and in a separate part of memory, q was pointing at the value y. That star means and separately, and is really important because it lets us reason about aliasing or the lack of it depending on what we might want. In this case, assigning z to p makes the value of p be z, but it leaves the value of q to be y, since they're not aliased. The lower left corner picture shows, as a picture, the footprints of these two formulas, which are disjoint. Whereas if the p and q are aliased, their footprints would overlap, and this aliased situation would not satisfy the precondition. With that in mind, here's the first take on what specs for malloc and free might look like. So the allocator, when you assign p gets the value from alloc, p is now a valid pointer to some memory. We don't care the value of the memory, but it should be some valid memory. The precondition here looks kind of funny, emp. It means true. No requirements before calling the allocator. but true with an empty footprint. So formulas have a footprint. The precondition for pre says P is pointing to some valid memory, so its footprint is that part of the memory. After calling free, you're back to just empty. Now, this by itself wouldn't be so interested. You'd like to call alloc in the context of some code that's maybe maintaining a hash table or some other data structures. We can reason as follows. So the first line here is the spec of alloc. So after calling alloc, P points to something. But that means that if Q separately was pointing to 6, afterwards Q is still separately pointing to 6, because the first triple here says that alloc will do its job without relying on any memory present. And so if there is some memory present, it won't be touched. And this is called the frame rule of inference and is crucial in using separation logic and scaling up simple local specs that talk about just what's relevant to a piece of code into the context where they might be used, where you might be maintaining some number of other data structures, and you want to know that those structures are still intact following the execution of, say, malloc or free. Here, if we ignore null for a moment, are the actual specs that we work with. MM here, the precondition for calling malloc, is a predicate that says the internals of the memory management system are in a consistent state. It's our invariant on the internals. And you'll notice here, it's a precondition to both malloc and free, and it's a postcondition as well. So the malloc and free code is guaranteed to maintain the invariance on the internal data structures. The postcondition here is that we get P pointing to some memory, but we also get a malloc token, which one way to think about that is it's sort of a capability or a witness that you got this address from malloc. And notice that that same malloc token is part of the precondition for calling free. When you call free of P, P better be pointing to some memory, and you have a malloc token, so in our reasoning we'll know how much memory that P is pointing to. Another way to think about it is the malloc token is abstracting it from the metadata. In our implementation, that's a word just before the user's block that gives the size. So the code of free checks that word to determine what is the size and act accordingly. So it's the per instance metadata, one could say. And having M token tells me that this is a valid pointer, even if it's a pointer to 0 bytes. So here are the final specs. After calling malloc, you know, is allowed to return nothing. So it either, no matter what, after calling malloc, the memory management system is in a consistent state. The MM invariant holds, and in other part of memory, either P is null, and we don't know anything about the memory per se, or we know that we have a malloc token, and we have P pointing to n bytes of memory. And if n is 0, fine, we still know it's a valid pointer. That's what our M token tells us, among other things. And it tells us it's one way to establish the precondition of free, because for calling free, you need P to either be null, or you need to have a malloc token and P pointing to that valid memory. We are not going to directly prove that our implementation satisfies these specs. Our implementation will be proved against a resource-conscious specification, which in turn will be proved to imply these more simple ones that capture the standard API. Here's, at the top of the slide is my naive attempt at a resource-conscious spec. So now the memory manager's predicate is called RMM, and it's parameterized on K, how many bytes that are available to be allocated. And the idea is, if you call malloc of n, and that's fewer than the K bytes that are available, malloc is guaranteed to return a result. You'll get your malloc token and P pointing to the memory. And the memory management system invariant will now be true of K minus 1. That'll be the number of available bytes. That's wishful thinking, though. So in this audience, everyone knows that the problem of fragmentation is quite challenging, and we won't be able to implement such a spec in any reasonable way. What we can do is make a slightly more elaborate and less abstract specification in which we have a resource vector that exposes conceptually at least, the free lists, the bins. And so the precondition here says, well, I have a resource vector V, and my request n, the corresponding bin is I. And V of I is positive, so I have at least one available block in the size class associated with size n. If so, after calling malloc, there is no null disjunct here. After calling malloc, you will have your M token, NP pointing to n bytes, and you will have an updated invariant that tells us we have the resource vector we had before minus 1 block in the size class I. To make effective use of these resource conscious specs, the code needs to make, how would we establish that we have the right resources? Well, we call one of the prefill methods in our extended API. These attempt to prefill the free lists. There's two flavors. One is ask the system to call mmap to get big blocks, chop them up, and pre-populate the free lists. Or the code, if we don't want to rely on an unverified mmap, we can call prefill providing the large slabs of memory as needed. So, for example, from the BSS space of the process. Here's what the specs look like actually in the VST notation. It's a bit elaborate, and I won't tell you about everything here, but the key thing is the pre and post conditions are broken into 3 parts. There's the SEP part, which is the separation logic part that has to do with what's going on in the heap memory. As you saw before, we have the memory managers invariant. It's actually parameterized on the global variables of the program, which give us access to the root of the data structure, the free lists and so forth. Then there's a local part of the spec which refers to the local variables. Here the local variable of malloc is its parameter n bytes. And what's the value initially of that local variable? Well, it's some mathematical integer n with which we'll be able to do our propositional reasoning and impose conditions such as that n is no bigger than a maximal unsigned integer, or a little bit less to allow for the fact that anything we allocate will have a little bit of overhead that gets wasted. Likewise, the post condition here says that afterwards you get the memory manager invariant, and you either get null or you get the malloc token and a memory block pointing to n bytes. The EWS here is a permission share, which is part of VST's reasoning to cater for multi-threaded programs. So although our allocator so far hasn't been verified for multi-threaded use, the system we're working in fact provides for that. The workflow to use the VST system looks as follows. So you define a functional model of whatever your problem is, some sort of problem-specific math. Here there's not very much math, a little algebra to deal with alignment and so forth. Then we define representation relations like my MM and RMM, invariants on the C data structures that connect them with whatever abstract model we're trying to implement. We write functional specs for each of the C functions, the internal ones as well as the APIs. If there are multiple specs, like in our case we have the resource conscious spec versus the resource oblivious specs, we prove subsumption lemmas that say if you satisfy one spec, you also automatically satisfy the other. Then we prove correctness lemmas for the function bodies. In this case we prove, for example, that malloc satisfies its resource sensitive spec, and then its subsumption lemma tells me it also satisfies the resource oblivious spec. In that proof, we make use of automated forward symbolic execution. And the user will, it's interactive. The user will be providing loop invariants and hints how to, when it's a good idea to unfold some definition, for example. At the end of the day, if we get QED, that means we have a machine-checked proof, which says that our program is correct in the CompCert's C-Lite semantics, that's its source language semantics, which is a very careful formalization of the C11 standard. This slide shows, summarizes the effort that went into this. The first column of numbers is the lines of C code, which is around 100, fairly small bit of code. The next line is lines of specification. You'll notice here we have some abstractions like defining the particular linked list structure used by our free lists and so forth. Not only making definitions, but proving lemmas about them, which are then going to be needed in verifying the actual code. And then we have verification numbers for the effort that it took to verify various bits of the code. All told, it took a couple person months on the part of myself, a new user of the VST system and so forth, with a lot of interaction and collaboration with Andrew. Whoops. The future prospects. We would like to verify implementation that could be used widely. Ours is perfectly fine for use in, say, embedded applications and so forth, where a sequential one is adequate. But we'd like to verify an industrial strength one. We have our sights set on ME malloc because it's a full-featured, high-performance system with some very interesting features to do with use of sharding in order to achieve locality, one of the critical ingredients of high performance. And it's relatively small, in only 3,500 or so lines of code. Of course, the more lines of code, the more verification effort. It would also involve lots of low-level C reasoning, which is takes effort in VST, but is in the ballpark of what we've already done. The slide lists, the 2 bullets indicate 2 particular points that would be challenging in this work. One is in the concurrency. VST supports sequentially consistent mode for compare and swap and other atomics, but MNEME makes use of release acquire mode and relaxed mode. So we would either have to switch MNEME at a bit of performance cost to use sequentially consistent mode, or we would have to axiomatize those or do other work, which is actually, there is ongoing research to address that issue. But for the moment, there's some gaps that would need to be filled. The other thing is dealing with shared metadata. Now, using the malloc token to abstract from the shared metadata is no difficulty, but in manipulating it, the code will need to do pointer int casts that are not valid according to the C11 standard and currently not supported by C CompCert. However, there's work in extending CompCert to cope with this kind of C code, which is sort of ubiquitous in practice. So there's prospects for solving that problem too, and we're keen to make that attempt in the future. In summary, what I've told you about is a malloc-free implementation that's compatible with the standard API, written in standard C, with amortized constant time performance for small blocks. It's been proved correct with a machine-checked proof in a foundationally verified program logic and verifier with a resource-aware spec for when malloc is guaranteed to succeed, and a proof that that resource-aware spec implies a resource-oblivious spec which captures the standard API in a precise way. Still to do is dealing with other features of industrial strength allocators, such as shared metadata and sharding and so forth, multiple threads. That's left to the future. Now I've come to the end and appreciate your attention. Time for questions. The image on the left shows the verified software tool chain and the components that include the application I talked about. There have been other applications like crypto components, and to learn more about this besides the paper, I would direct your attention to deepspec.org. Thanks.
Right, let's thank the speaker virtually again, and we actually have both David and Andrew with us in panelist here. So anyone who want to ask questions, please do in Slack or either raise your hand using the Zoom feature. And before we do that, I also wanted to remind everyone that we'll be returning back to the Q&A section for the first paper after the Q&A section of this paper. All right. I think I'll give people a few minutes to type their questions, but I will start with my question for this paper. So David, I think coming out of the keynotes earlier, I think there's a shared vision between this paper and what Richard advocate for. And can you comment on how you enable more researchers into this domain, and what are the essential tools or knowledge for them to start doing research in this similar manner?
Well, I mean, the domain he talked about involves using a pretty automated tool. And by now there are quite a lot of good tools in that class and tutorials and so forth for people to be able to get up to speed pretty quickly. At my university, we teach the standard concurrency course. We teach specifically using the spin model checker, so engineers find that fairly easy to pick up. The work I talked about is sort of at the other extreme of the spectrum, that it requires a significant amount of user interaction and so training. However, fortunately, the VST system by now has good tutorial materials. In fact, there's presentations in connection with PLDI that maybe Andrew wants to speak about.
Sure. So in the REMS Deep Spec workshop yesterday, I talked about VST and gave a demo, and the video of that talk is available at deepspec.org. But also for researchers and even engineers to get into this business, the first thing you'd want is a good interactive tutorial on the Coq Proof Assistant with exercises. And that's existed for several years now. It's called Software Foundations. It comes in several volumes covering sort of the basic logic, applications to reasoning about programming languages, which is not so relevant here, applications to reasoning about algorithms, functional algorithms, but also there's a new volume that's in beta now for verifiable C, doing these kinds of separation logic proofs about C programs. So the system is available open source. There's all sorts of reference manuals and tutorial materials for it. There's video demonstrations. As David says, it's a little more work to get into this kind of verification than the use of the spin model checker, which is certainly a valuable thing itself, but it's certainly possible.
Thanks for your answers. And I actually want to follow on the art kind of like different aspect of this work. So you kind of mentioned this is for sequential Malloc free, and what prevents you guys to move forward for parallel workers or parallel Malloc free?
Right. So, step one, parallel garbage collectors are just bigger. And in some sense, the verification effort is proportional to the size of the program. And this is where we started. Our program logic for C is for concurrent threads, but there are many levels of programming concurrent threads. There's semaphores, a very traditional model dating back to like 1968. And we have a concurrent separation logic for semaphore-based programming. Then the next level up is sequentially consistent atomic C11 operations. And indeed, our concurrent separation logic can support that too. So to verify a multi-threaded malloc-free system with, for example, a separate free list array for each thread and cooperation between the threads and so on, would be very feasible. But right now it'd be most feasible in a sequentially consistent implementation, which is going to be, as David said, a little bit lower performance than, let's say, the release acquire mode. Working on release acquire mode concurrent separation logics, we know where to go with that. There's research in that area. So, but it's not really supported in the tool just yet.
I see. Okay, that sounds like a very exciting future work then.
Yes.
So I think I'm looking at Slack channels, and people might have their question answered in the earlier section. So, Ben just raised her hand, and let me just enable. Okay, Ben, can we talk now?
Yep, I think so. Can you hear me?
Yes, I can hear you, please.
Great. So as somebody who just finished working on a concurrent collector, I can say that clearly there's need for verification tools. But I do wonder, it seems like the cost here is quite high for like an industrial project. I find, it's hard for me to imagine, given the power to weight ratio of the sort of foolproof technique here, that you'd be able to justify that in an industrial project. So I wonder what sits between, and on the other hand, the approach that Richard described earlier is pretty, you have to really abstract away most of the implementation to get the real core of the idea before you can start verifying it with model checking. So I wonder what sits between these two. Is there something that you can potentially?
All right, so that's an excellent question. I will say that the VST tool has been used to verify a high-performance generational collector for a pure functional language. Not one of those imperative functional languages like Haskell with all its thunk updates. So in other words, it's a generational garbage collector without support for mutable references. And that's not by us, that's by Aquinas Hobor and his student Xingyi Wang at National University of Singapore. And their next project is to enhance it with mutable references. So that's not quite industrial size, but it's an actual garbage collector and not just a malloc-free system, and it's been fully verified. Now, what Richard Jones was talking about was making a functional model of the system that you could write down in the language of the spin model checker and verify the high-level properties of this functional model, and then sort of eyeball that the functional model corresponds to the C program. Now, what we do all the time in verifications of other systems besides this malloc-free in VST is we make a functional model described in the logic of the Koch theorem prover, either as a functional program or as some sort of inductive relation or as any other mathematical model that you'd like. And we prove that the C program is a refinement of the functional model. That's VST's real strength, so that the correspondence between the model and the program is foundational and machine checked. And then in Cox logic, in a way that has nothing to do with C or with VST, we can prove that the functional model has the high level properties you want. So that's the proof that sort of Richard Jones can model check, and we would have to prove interactively in Coq, but that proof does not mix up all the complexities of C, that it layers very well in that sense.
Thanks for the answer.
I don't know what Ben understands. Andrew, can you explain the difference a bit more? I'm trying to understand what you said.
Okay, so the second part about functional models versus C programs. Think about the difference between an algorithm and a program. You know, in an algorithm textbook, they'll write an algorithm in pseudocode and prove the algorithm correct informally. And it's sort of up to you to see that your program correctly implements the algorithm. And that's fine for the algorithm in the textbook, but real programs are quite complex. And even if you could prove that today the program implements the algorithm, the program is going to be maintained. And by next year, who knows? So it's very important to do both kinds of verifications in a machine checked way. First, that the program correctly implements the algorithm. That's what VST is really good for. And second, that the algorithm has the high level properties for correctness that you would want. Now, in the work that David just presented that we did, the functional model is not that complicated, right? It's just an array of free lists. So there wasn't that much to say about it, and the verification of its properties wasn't that difficult, so we didn't focus on it. We focused more on the proof that the C program exactly, correctly, machine checked implements the functional model. But in other application domains where the functional models are more intricate and the properties they have to satisfy are more intricate, then you really want two separate proofs. And it's really good that the logic can modularize these proofs apart from each other so that the details of C don't get mixed up with the model level proofs and vice versa.
I see now, thanks. And this VST is the tutorial you did yesterday.
Yes.
Thanks.
The one, if you don't mind, if I follow up to that. So the one thing that I might add, though, is that now sort of the premise of my original question was one of cost, and in particular the degree of assurance that you get versus the cost of getting that assurance of correctness.
Okay.
And I wonder if there is if you could settle for slightly less assurance, but still have an implementation-driven sort of, not proof, but checking. So static analysis is one potential option tool. Then if there are any tools that you know of that sort of provide that lesser degree of cheaper assurance.
Well, let me put in a plug for a paper that was mentioned in the first session and should have been in our list of related work, which is work by Hoblitzl and Bertrand, verifying collectors using the Boogie tool chain. So they're relying on SMT solvers, so automated proof rather than interactive proof. And they're relying on untrusted components to make the connections between some code and some assertions written in it versus the conditions that are actually being checked by the automated untrusted theorem prover, right? So at the end of the day, you don't have an end-to-end proof that the code is actually correct. On the other hand, you have a pretty reasonable assurance argument that, well, we've done a lot of careful specifying and reasoning. We have expressed some key invariants or the abstract models or protocols or whatever, and we've proved some things to the extent you trust the prover, which look pretty darn likely to be related to the verification conditions for our code, right? So it's not as high level of assurance as is being achieved with the VST tool chain. But on the other hand, as they demonstrated, it's considerably less work. And in particular, the interface to the tool is very much focused on the code and annotations, which tend to be easier for engineers to pick up. So they're not directly structuring the logical reasoning. That interface is often annoying and problematic as well, because you sort of know it should be true, but the only way you can tell the system something is by putting in assertions. So it has its stronger and weak points, but in terms of the options for an organization that's looking to doing something to improve their assurance, but isn't ready to invest to go the full way, that's something to be aware of. And in particular, in this space, I would suggest looking at that paper. It's cited in the Slack channel.
That's very helpful. Thank you.
Paul, can I just follow up with one more question?
Yeah. Yes, definitely. We have some time.
So Ben's question about what's in the middle. So if I take what Andrew explained, then does it make sense to connect VST with model checking instead of what you're doing with in this paper with theorem prover?
Well, without any formal connection, just using lightweight tools like software model checkers is a way that one can get some understanding about your system and how to describe it. What are the requisite abstractions? What are the key invariants? At least up to a first approximation, right? So as a step in a process that then might later be followed up by doing a more careful formalization, you'll likely discover that there were a lot of things that were wrong because of the tool's abstractions and so forth, but it could provide good guidance. So there's already possible informal connection in terms of people's processes. As to a formal connection with it, I'm not sure I have any particular thought on that.
I will say this though, sometimes it's already very helpful just to write down the functional model, which, you know, for many of our verifications, writing down the functional model is not that hard. It's no harder than Haskell programming, which, you know, any master student can do, because the functional language inside Coq really is a lot like Haskell. So sometimes it's proving the properties of the functional model in the mathematics of your application domain that's challenging. But that really depends on how complicated your application domain is. In sort of sequential malloc-free, it's quite simple. In a concurrent collector with gray and black and white, as Richard explained, it's not trivial. But the proof that your C program properly implements the functional model can still be very useful, even though we don't have formal proofs about the functional model itself.
Thanks.
All right, we have lots of great questions. So let's thank the speakers again. Thank you, David and Andrew, joining us here. And before we conclude, we actually will move back to the Q&A section for the first paper, exploiting inter and intra-memory asymmetry for data mapping in hybrid tiered memories. So we have Anab here with us, and for anyone who has questions that did not have a chance to ask during the first Q&A section for the first paper, please feel free to do so now, either in the Slack channel or raise your hand in the Zoom session. And I will actually take this opportunity to ask questions first. Anand, can you hear me?
Yes, I can hear you.
Great. So in your paper, you're targeting the asymmetries between DRAM and NVRAM. And there's also actually asymmetries in NUMA systems. So can your work be extended to handle NUMA systems as well? And how will you do that if so?
Right. So what happened for now, we have considered the DRAM and non-volatile memory in the form of phase change memory, which has some asymmetries. But using these bitline segmentations that we propose in the paper, we have actually created a non-uniform access latencies within each memory type. That means if we consider only DRAM, then the access latency varies based on what memory address you are trying to access through your program. So inherently, using this new kind of memory architecture, we have created a NUMA-like situations within the existing memory hierarchies. So to answer your question, yes, the technique that we have proposed will work for any numer-like systems because we have inherently created such architecture using the current memory hierarchies that are known in traditional architectures.
Okay, thanks for the good answer. And I will actually follow up with that. So seems to me that your work has kind of more fine-grained classification between memory levels. And do you think that in the future we'll have even more layers of in the memory hierarchy? And if so, how would you say partition the work between hardware, operating systems, and programmers to perform the tasks here? I know that in your work, it's mostly in the operating system level, but how will you approach the problem if we have even more layers in the future?
Right. So if we add more asymmetries, for example, right now we have considered only the near segments versus the far segments. So essentially creating two segments within each bank, but we can go even more. That means we can have more than one segments or more than one layers, as you are saying. The only complexity that arises based on that is in terms of maintaining the different information or access latency information for each of these segments, which is currently stored in a kind of a table inside the memory controller. So we can handle any number of layers, but the complexity or the price paid will be additional hardware support needed to store the latency and reliability informations of these memories within the memory controller. So your memory controller will grow in size, but there you can have many more layers than what we have currently considered.
I see. That makes a lot of sense. Thank you for the answer. Okay, let me look at the Slack channels and see if there are any questions from the audience. And if people have any questions for the first paper in the section, you can also just raise your hand in the Zoom channel. All right, if not, then let's thank all the speakers again for this wonderful section. And I will leave the stage for our general chair and program chair, Martin and Chen.
Thanks, Paul. We finished almost exactly on time.
Thank you, Paul, for chairing this session.
Okay, Martin, how do we want to do this?
Let's see. So this brings us to the end of the structured part of ISMM. Thank you all for joining. Let's do two things during this part of the conference. First of all, let's thank everyone who helped organize this. Let's starting with the authors. Like a conference wouldn't be possible without submissions. And so we want to thank all the authors, both of accepted and of not accepted papers. This is what makes a conference like this interesting. And I think we had a number of really exciting talks and lots of discussions based on the work. We'd also like to thank the PC and ERC members who's done an enormous amount of work putting this program together, as well as the steering committee, who's helped a lot behind the scenes. We'd also like to give a shout out once again to our student volunteers, Ahmad, Radu, and Wes, who really made this possible. It would have not been possible to put together this conference without all their hard work. Thank you also to our session chairs, Eris, Ian, Poan, and Stefano. And finally, thank you to everyone who volunteered for one-on-one meetings. This, I think, was also a part of the conference that was very appreciated, especially by students. And I think this was fantastic that so many of you volunteered. And finally, we'd also like to thank the PLDI organizers who put together a lot of the infrastructure that we as ISMM could rely on, such as the Slack channel, setting up the webinars, and so on. So a lot of thanks to that group of people that's also very large.
And I totally concur, can't say it better. And thanks, Martin.
And you left a couple of people out. Let's thank the conference chair and the program chair for their great work as well.
Woohoo!
Yep.
Thank you.
Most welcome. So, Martin, you had some statistics that you plan to share.
Yes, I thought I'd share a couple of statistics about this conference. This was the first virtual ISMM, so things were a little bit different. But this being a virtual conference also means that we have real-time metrics about how it went. And so the live stream this morning had 1,541 viewers, which is great to see lots of people interested in the conference. We had overall 77 people who joined the webinar, either as a panelist or an attendee throughout the day. And we also had a lot of one-on-one meetings that were scheduled as part of this process, 71 in total that were scheduled. I think it's great to see this much engagement from the community, and thank you all for participating and joining the conference. It was a lot of fun, and I hope we had some great discussion. And the conference is not over yet. There's going to be a breakout room that's going to be open. This is going to be the new trends in memory management room that we'll just reduce it to one room. So some of us will be there, and please feel encouraged to join and chat a little bit more. Also feel free to chat more on the Slack. And we also, I think, have a few more one-on-one meetings scheduled.
So I had great fun at the last breakout room. There was only one room with people, but there's 8 to 10 people. The Wentel, that's our presenting author, and Albert, so 2 of them were there. People walking in that I didn't even know that they actually listened to the conference. They all recognize Wentel and Albert. So it's definitely the exposure is there. So it was a lot of fun. Thank you very much for everybody. This is my first virtual conference. I'm very happy and very happy now. We have accomplished. We are done.
Good night, everyone.
Right, thank you. And hopefully see some of you at the rest of PLDI as well.
Enjoy the rest of the conference.
Thanks, everyone.
Bye.
Cheers.